Okay, everybody, here's the class notes for day 6. We began by talking about some basic properties of logarithms and the 3 basic laws of logarithms. First, the properties. These are kind of things that are just good to say. They're, in a way, kind of obvious, most of them, but anyway, like log base b of b equals 1 because b to the first equals b. Log base b of 1 equals 0 because b to the 0 equals 1. So it's nice to have expressions that equal 1 and equals 0. Those are good things to know. An extension of this idea here is that log base b of b to the n equals n. So anytime the argument and the base are the same, whatever that exponent is, and there is a 1 right there, same thing, but whatever that exponent is, it just equals that exponent. This is a little bit odd here, so just kind of check this out. B to the power of log base b of some number always just equals that number. Okay. Then we got into the basic 3 laws or rules of logarithms. First one, product rule. Log of a product is the same thing as the sum of 2 logs. Okay, and it goes both ways. If you had a sum of 2 logs, you could write it as a log of a product. So a couple of examples there. Pretty simple rule to say and work out. The difficulty becomes when it gets mashed up with other rules as well. But anyway, there's the product rule. The quotient rule is just kind of its own inverse. So log of a quotient is the same thing as a difference of logs. Okay? Be sure and be real careful here. This is not log of a plus b or log of a minus b. Don't do that. It's the sum of the 2 logs, log of a plus log of b or log of a minus log of b. Okay? Couple of examples working those 2 rules together. Okay, and simplifying them as much as we could. Here's a sum of 2 and a difference there. So this log of 2 being subtracted goes on the bottom. Okay. Here, now I got to back up for a second because I didn't have those parentheses there to start off with. Okay. So just 3 things here. Natural log of 5 minus natural log of y plus the natural log of 2. Only the natural log of y is being subtracted, so that's the only thing that goes on the quotient. The 5 and the 2 are both positive. They're being added, so I multiply 5 times 2. Now, if I had put parentheses around these last 2 things, subtracting the group of the 2 of them, the answer would be this right here, natural log of 5 minus 2y. But we didn't go there, so don't worry about it. Okay, next page is your final log law. And it is called the power rule, all right? Or sometimes people call it the wraparound rule because it looks like this. When you have log of a power, you can take that power and wrap it around as to be a coefficient of the log. So log of n to the a equals a times log of n. Pretty nice. Log of x squared is 2 log x. 1/2 natural log of x, because x to the 1/2 is the same thing as the square root of x, can be written as natural log of square root of x. All right, so there's your power rule, and all 3 of those rules are going to get mashed together in various ways in the practice set. Also, you'll see a few examples of this thing called the change of base rule, which says that any log can be written in terms of any other log base. Any log can be written in any other base. It's kind of an intimidating looking little equation in general, but in practice it's pretty easy. Log base 2 of 15 is log of 15 over log of 2. Any base, natural log base 11, whatever. You can also write functions this way. If you wanted to graph the function y equals log base 3 of x, you could write that as natural log of x over natural log of 3, or log base 10 of x over log base 3. It doesn't matter. Change of base rule, pretty cool. Now I had one super gnarly example out of the practice set that we did. So you can go back and check this if you want when you get to number 35. Solving equations was the next thing we talked about. Talked about 2 different kinds of equations, exponential equations and log, excuse me, log equations. There's an exponential equation where our unknown is an exponent. A log equation generally has the unknown as part of the argument of the logarithm. So we'll get to these in due time. Here's an exponential equation. The way you unwrap the exponential equation, that is undo the exponentiating, is to take the log. So logarithms undo exponents. That's why we need them. So you take the log of both sides of this equation, and then with our wraparound rule, this x becomes a coefficient of log of 5. And so then after you write it that way, take the log of both sides, Then use your wraparound rule there to get the exponent isolated, and we just divide log of 12 divided by log of 5. This is the exact value of x. This, on my calculator, I got 1.544 as an approximation. It's pretty close, depending on what we're doing, but it is a little bit wrong, so just make sure you recognize that. Okay, I'm going to come back to this, well, actually come back to something we did a little bit earlier. To show you how things are connected, 5 to the x equals 12, you could write that as a log equation. Log base 5 of 12 equals x, because that equation right there is saying the same thing. 5 to the x equals 12 with this little snail pattern. All right? And I hope you might have recognized that the change of base rule is this. This is log base 5 of 12. Well, you could write that as log of 12 over log of 5 with the change of base rule. So these things are connected here. Okay, I'm going to do a slightly more complicated one with exponential equation and give you the general algorithm here, which is this. Solving an exponential equation, you isolate the exponential expression part first, and then use logarithms to undo the exponent. Here's a slightly more complicated exponential equation. 1.06 times e to the 0.5x all divided by 5 equals 10. Well, we have to isolate this exponential part, which is just the base with the exponent. Okay? When we get down to here, we've isolated the exponential expression. So I multiplied by the denominator, I got 50 over here now, and then I divided by 1.06, and so I got e to the 0.5x equals 50 over 1.06. Now I take logarithms, and not before now, but now I do. I'm going to take the natural log, because the natural log of e is 1, and that just disappears. Notice I'm not dividing. I'm not using the calculator to come up with this. 50 divided by 1.06. Just going to keep it pure and unapproximated. So I have 0.5x equals natural log of this. I get rid of the 0.5 by multiplying both sides by 2, and there's my exact expression, which is approximately 7.708. Okay? Don't do the approximation until the very last part. That way you get your answer as precise as possible. Log equations can be quite simple, actually. You just use the snail to unwrap the equation and write it in an exponential form. So that example that we had a little while ago, log base 3 of x minus 5 equals 2, just write it in exponential form. 3 squared equals x minus 5, and you get 14 pretty quickly. Sometimes it's more complicated, though. If you have two logs, you should combine them into a single log using your log powers, and then unwrap. So x times x minus 1, 10 to the first power, that's 10. So now I got a quadratic. It's not so nice. I got to use a quadratic formula, daggone it. And I get two answers from the quadratic formula from this expression, 3.702 and negative 2.0702, excuse me. And we have to keep in mind that a logarithm is only valid for real numbers when the argument is greater than 0. Greater than 0, positive. So this negative x value does not work in this expression. It doesn't work in either one of them, actually. And so we have to toss this one out. The only solution is 3.02. So we've tossed that one out, and our only solution is 3.702. That's our answer. Okay? All right. And I think that's about it. Or was there one more thing? Oh yeah, one more tiny little example about log equations is this. If you have two log expressions on either side of the equal sign like that, that's only true if the arguments are the same, okay? So if natural log of x plus 3 equals natural log of 2x, well, that must mean that x plus 3 equals 2x. And so you get your answer pretty quickly that way. Okay, that's it. Bye-bye.